In this video, we'll study a very important concept known as the Barkhausen's criteria for oscillations. In the next few videos, we will be designing oscillators which will give us the sine wave as an output, which we have been using as an input so far. For this, there are some conditions that need to be met which we will see in this video. Till now we have been using op-amps and feedback. We saw that negative feedback gives us control over the gain and positive feedback just makes the output saturate, which we used for designing comparators. Let's look at the concept of feedback a bit more closely. Consider the following configuration. It is basically our feedback configuration but with a broken loop, that is, the output is not fed back in. Let us now apply a sine wave as input to this configuration. The output of the amplifier is equal to A times sine omega t. The output of the feedback network is A, beta of omega into sine omega t. The output of the mixing network at terminal 2 is minus A beta of omega times sine omega t. The loop gain can be said to be minus A beta of omega. If this loop gain is negative, then we have negative feedback which we have used a lot. But if it is positive, then we have positive feedback. Let's explore this case a bit and assume that the loop gain is positive. That is, A beta of omega is negative. Now, let's throw the switch to terminal 2 and see what happens. Say the loop gain is greater than 1. In this case, we see that the input at the amplifier goes on increasing as an amplified output is fed back as the input. Hence, the output of the amplifier goes on increasing and finally saturates. This is not of much use to us. Now say the loop gain is less than 1. In this case, we see that the input at the amplifier goes on decreasing as a smaller and smaller portion of the output is fed as the input to the amplifier. Hence, the output goes on decreasing and the sine wave dies down. This too, is not of much use to us. Now consider the final case where the loop gain is equal to 1. That is, for some frequency omega naught, minus A beta of omega is 1. In this case, the input remains the same. That is, sine of omega naught, and therefore, the output remains A into sine omega naught. So, it looks like even if we remove the input, the circuit keeps on generating a sine wave. Well, this is exactly what we want. An oscillator generates the sine wave without taking any input signal. So, if we design the feedback network such that the loop gain is 1, that is, minus A beta is 1 for some frequency omega naught, then we get sustained oscillations of the frequency omega naught and our oscillator is ready. So, the requirement is minus A beta of omega naught equal to 1. This condition is known as the Barkhausen's criterion for oscillations. This can be broken down into two conditions. The loop gain phase shift should be 0 or some integral multiple of 2 pi. The second condition is that the magnitude of the loop gain has to be unity, that is, 1. The first condition is used to build the feedback network for obtaining oscillations of a particular frequency. The second condition provides the minimum amplifier gain for sustained oscillations. Now the only question that remains is about the initial oscillations. How to provide those? The answer is quite surprising. We simply don't provide any initial oscillations. Whenever we switch on the power supply, the transients produced contain a number of harmonics. The one with the frequency omega naught, that is, the oscillating frequency, is picked up by the amplifier and we get our sinusoidal output. Another source of these initial oscillations is the thermal noise present at the input. It contains all the frequencies and hence provides the initial oscillations. In this way, by putting the op-amp in positive feedback we can build oscillators which give sustained oscillations of a particular frequency. That's all for this video. If you have any questions, feel free to ask in the comments section below. Don't forget to like, share and subscribe.